every now and then we're bound to look at our dry planet neighbors and wonder, where the heck did Earth get all its water? Well, that is exactly what I'll be talking about in today's video. Before we jump right into the video, I want to thank the sponsor of today's video, Brilliant. Brilliant offers tons of amazing and interactive courses online, which I will talk about at the end of the video, and give you a special offer so you can go check them out. Okay, back to how Earth got water for now. First, we kind of have to start with where it all began. I'm going to say the disclaimer up front that I am Geo Girl. I know about Earth, I know about geo processes, I know about geohistory, and I'm not Astro Girl or Space Girl or Universe Girl, so I don't know all that much about astronomy, astrophysics, how the solar system came to be based on a physics background. So if I get anything wrong or leave out any details that maybe you and my audience know better than me, please comment below. I mean, politely, but please comment below and fill us all in on what I left out. With that said, I'm going to talk just, about the basics behind how the planets formed and kind of the distribution of different materials in the early solar system protoplanetary accretion disk, to get a sense of kind of where the water was and where and when it was potentially being transported. So first things first, the planets in our solar system formed from a protoplanetary, before planets, accretion disk, a disk of material that was swirling around in space where planets were beginning to accrete. Accretion is kind of this way that material comes together and then it gains more and more mass and more gravity and pulls more material in, and that's accretion, to my understanding. And this accretion disk contained a lot of really tiny particles, but mostly gas. The disk originally was 99% gas by mass. So water was mainly present as water vapor, and in some cases ice coatings on tiny dust grains. Water was very abundant within this disk, but because of the heat of the newly forming star at the center of the solar system, our sun, that was kind of creating this temperature gradient in the disk that pushed out all the more volatile substances like water to the outer parts of the solar system, or at that point, the disk. This caused the formation of the giant gas and ice planets that we know so well in our outer solar system, while the tinier rocky planets formed in the inner solar system, where it was mainly rocky rather than icy and gassy material. So Earth and the other rocky planets formed from accretion of silicates, basically minerals that contain silica, which is silicon dioxide. But geochemical evidence does suggest that Earth's ocean formed very early in Earth's history. So it's not like it was water that accumulated from impacts over 4 billion years. It was pretty much there and pretty much done accumulating for the most part by 4 billion years ago. So where did all this early water come from? Well, I was originally taught that there were two main hypotheses, and I'm saying originally taught because I'm going to talk in all of the following slides about why these two main hypotheses kind of need to be explained in a better way. In other words, in previous videos, I have not explained them, I don't think, fully correctly, and I'm going to try and correct that here. So these two major hypotheses that I kind of used to be taught and teach myself include outgassing, first and foremost, which basically meant the volcanic release of water vapor and other volatile substances and gases like carbon dioxide, nitrogen compounds, hydrogen, helium, other volatile gases that came out of these volcanoes and kind of made up our early atmosphere. From that atmosphere, the water vapor eventually condensed to form our oceans once Earth had cooled down enough to allow this condensation. This makes sense because there was a ton of volcanism on this early, really hot, molten Earth. The second major hypothesis is that the water was delivered from asteroid and comet impacts. This also makes sense because early on in Earth's history, there were tons of impacts compared to today, very early in Earth's accretion and formation. But if we really think deeply about this first hypothesis, the outgassing one might wonder, okay, but where did the water within Earth come from that allowed volcanic release of water? Well, a lot of people don't know that rocks can contain water within their molecular structures. These are called hydrated minerals. Our mantle contains a lot of hydrated minerals, and these hydrated minerals then become dehydrated upon melting, and this dehydration leads to the release of water vapor out of volcanoes, along with a lot of other dehydrated gases from those materials. So the assumption here for hypothesis number 1 may be that hydrated minerals accreted to form Earth. There are many types of hydrated silicates, for example, so maybe these were the minerals that accreted to form Earth, and then once Earth had formed and all that volcanism was occurring, the water vapor was released upon outgassing. Assuming that Earth's hydrated mantle source, in other words, the hydrated minerals within the mantle, sourced our oceans through outgassing and then condensation, one might wonder, does that mean that we're out of hydrated minerals in the mantle today? Have we used them all up? Does water vapor still come out of volcanoes, or is the mantle completely dehydrated? Actually, it's not even close to completely dehydrated. Estimates suggest that hydrated silicates in the mantle contain 1 to 10 oceans of water. That is, when measuring in number of Earth's oceans. So 1 to 10 oceans exists within the interior of Earth. And I've seen estimates even up to 50 oceans, but I think that's on the pretty high end of estimates. So in any case, it's not fully dehydrated. However, where this abundance of hydrated minerals in the mantle came from is another question. Like I mentioned, one might assume that hydrated silicates were the things that accreted to form Earth, but this actually doesn't work with models of the early solar system, which show that this inner rocky planet region of the disk was too hot for hydrated minerals to be stable and, exist and accrete in that region. So no, hydrated minerals didn't accrete to form Earth. It was all dehydrated minerals that accreted to initially form Earth. So does that mean that only the impact hypothesis works? The water must have come from impacts that delivered the water, which then hydrated the minerals within Earth that differentiated into Earth's now layers, which includes the mantle? Well, this is one idea of where the hydration came from. That is, hydrated phases like phyllosilicates, which are hydrated silicate minerals, came from the asteroid belt where these minerals are pretty common. But another hypothesis brings us back to the accretion idea, that hydrous phases, or water, could have been included somehow in the materials that accreted to form Earth initially. This is not a hypothesis saying that hydrated minerals accreted to form Earth, but rather the inward migration of such hydrated minerals led to their dehydration and subsequent immediate reabsorption of that water onto other grains present in the rocky planet region, which then accreted to form Earth. So in English, hopefully if I'm translating this correctly, I think it means that upon dehydration of the hydrated minerals within the rocky planet region of that early protoplanetary accretion disk, that water that was released from the hydrated mineral became adsorbed, which adsorption is just a process similar to absorption, but it's more of a surface thing than an entering thing, so it just gets stuck onto a surface basically. So that water adsorbed onto these grains, so it interacted with their surfaces and got stuck on there. It's not, as strong an interaction chemically as absorption, but it is still involving molecular interaction, so it's relatively strong enough to keep the water on there. And then these grains that had the water on their surfaces accreted to form Earth. But neither of these hypotheses fully work in order to perfectly recreate the chemical signature or isotopic composition of Earth's water. In other words, the hydrogen isotope composition within water from asteroids from the asteroid belt, for example, it's too heavy to account for the more lighter hydrogen isotope signature of Earth's water. So what does all this mean? So I talk a lot on my channel about isotopes. You guys know I'm a geochemist, so I tend to incorporate them in most of my videos. But let me back up and just re-explain kind of what an isotope is and why it's helpful for tracking where Earth's water came from. So each element on the periodic table can have multiple isotopes in which These isotopes have the same number of protons, because that defines the element, but a different number of neutrons, which in fact changes their mass. So if we look at hydrogen, for example, hydrogen typically has one proton and one electron. But there's an isotope of hydrogen called deuterium that has a proton, a neutron, and an electron. So this extra neutron within its nucleus leads to basically twice the mass that the quote-unquote normal hydrogen has. So we can basically measure signatures of hydrogen, oxygen, nitrogen, and other isotope ratios. In other words, the ratio, for example, of deuterium to regular hydrogen in Earth's water versus meteorite water to see if they match. Matching isotopic signatures or isotopic ratios of deuterium to hydrogen or heavy oxygen to light oxygen suggest a matching origin. So if we look back at the scenario that I mentioned earlier, the asteroids from the asteroid belt have water that has hydrogen that's relatively too heavy, so too much deuterium relative to regular hydrogen, compared to Earth's water, which contains relatively lighter hydrogen. In other words, relatively lower deuterium to regular hydrogen ratios. What might work to explain the slightly lighter hydrogen isotopes in Earth water is a solar wind hypothesis that suggests that solar wind, which is like 95% hydrogen, produces water molecules upon interaction with small bodies like asteroids, and the hydrogen in these solar wind created water molecules is actually lighter isotopically than typical asteroid water. So it may have been that solar wind derived water on these smaller bodies then got transported to Earth upon impact. And this might explain the slightly lighter isotopic signatures in Earth water compared to typical asteroid water. Overall, it's likely that Earth's water came from a combination of isotopically light solar wind-derived water and isotopically heavy non-solar wind-altered meteorites and any adsorbed water that may have adsorbed onto the grains that accreted to form Earth. One more potential hypothesis or process that potentially contributed to some of Earth's water that I hadn't heard of before is this idea that early on Earth, when it could have had a full magma ocean at its surface, this magma ocean reacted with hydrogen in the primordial atmosphere to form water. So in this scenario, it's not necessary that hydrated phases accreted to form Earth, or that hydrated phases migrated inward into the rocky planet region and then dehydrated and the water adsorbed onto grains that accreted Earth, or that water was transported from the asteroid belt. In fact, this scenario requires no delivery of water whatsoever, but rather just the interaction of the silicate magma ocean with hydrogen in the atmosphere. But based on the references that I read, which are linked in my description below, it seems that this reaction likely couldn't have accounted for just the amount of water within Earth's interior and at Earth's surface. Also, I don't know if I read anything about this, but kind of based on my logical thinking about this scenario, is that hydrogen, was mostly pushed out to the outer solar system during that early accretionary disk planet formation time. So could we even have had that hydrogen-rich of an atmosphere early on? And if we did, wouldn't hydrogen have been so light that it just escaped to space relatively quickly rather than reacting with the magma ocean? I don't know. These are just some of my thoughts. So this is just another potential hypothesis that may have contributed some water, but likely not all Earth's water. But with all of this potential delivery of water to Earth and potential formation of water on Earth, why don't the other rocky planets around us have water? Well, this is a major misconception because they do, / if they don't currently, or if they don't have that much currently, they did. Mercury is a little bit of an exception to this because it's so close to the sun, so it's relatively dry, except for some ice at the poles, which was likely delivered by impacts. Venus, on the other hand, is thought to have once been pretty wet, but underwent major water loss through hydrodynamic escape of that water and/or impact-driven desiccation. Likewise, Mars is also thought to have once had a lot more water, but also underwent major water loss due to atmospheric loss from sputtering. Sputtering, to my understanding, is kind of a solar wind-driven process where it kind of destroys the atmosphere, and then once the atmosphere is destroyed, the water just escapes. Correct me if I'm wrong in the comments. But it is also my understanding that Mars still does have not as significant amounts of water, but it still has water, mostly in the form of ice. But I'll talk in a future video someday. I still am promising to do someday a Mars or multiple Mars videos, so keep an eye out for Mars-related content. But overall, other than just general curiosity, why do we care? When Earth got its water, how Earth got its water, how water may have been obtained by other rocky planets and then lost. Why do we care about all these early solar system processes? Well, understanding how and why Earth got water and retained it is really important when we're looking at exoplanets, planets in other solar systems that may be analogous to Earth in its position relative to its star, because we need to know whether that planet has water to know how likely it is to have life, at least life as we know it. It also helps us understand the history of our solar system and why some planets or moons obtained water, retained water, lost their water, etc. Because again, it all comes back to habitability mostly. There's other reasons, but mainly habitability and whether worlds are habitable and how long they might be habitable for, etc. Because, we want to find life out there. But briefly, before I finish out this video, I really want to talk about potential problems that we face when trying to determine where Earth's water came from. Because like I talked about earlier, isotopes are really important for tracking where Earth's water came from, specifically for understanding what the isotopic signature of Earth's water is and what potential source of water, it matches isotopically, because then that can tell us where Earth's water came from. But for this, you might imagine, we need to understand the isotopic signature of not just Earth's ocean water, but Earth's bulk water. There are many water reservoirs on Earth, including not only the ocean, but also water vapor in the atmosphere, or water tied up in ice, or hydrated minerals within Earth's interior in the mantle, or even in life. As you guys have probably heard the stats, we are made mostly of water. So water is present in all of these different chemical reservoirs on Earth. But you might also be wondering, well, why does that matter? Shouldn't the isotopes be distributed equally across all these reservoirs? Well, no, because isotopes differ by mass, they can become fractionated or kind of distributed differently based on their mass. So for example, water containing light hydrogen has the tendency of evaporating more easily, whereas water containing heavy hydrogen stays behind in the ocean. So the atmospheric water reservoir might be lighter isotopically than that of the ocean. Likewise, oxygen isotopes undergo the same evaporation fractionation. And in fact, because of oxygen isotope fractionation in dynamics, it turns out that most of the ice at the poles contains water with very light oxygen isotopes relative to that of the ocean. So again, there's isotopic fractionation occurring with both the hydrogen and the oxygen isotopes in water all throughout Earth's water reservoirs. We can kind of get around this and try and measure quote-unquote bulk Earth water, or water that is representative of all of Earth's water, by measuring and averaging Earth's ocean water isotopic signature from, different samples taken around the globe and at different depths and at different types of ocean basins, etc. We can also measure and average water from the atmosphere in different locations, latitudes, and altitudes, and we can even measure water from Earth's interior, that is, from magma. But potentially the most important water that we can measure, that might be the most representative of bulk Earth water on an early Earth, is water from rocks. Yes, again, there are still many hydrated rocks on Earth, and a lot of them aren't even in the interior. A lot of them are right here on Earth's surface. And many of these rocks are really old, and the older we can get, the closer we can get to what bulk water was potentially like, isotopically, on early Earth. But another potential issue, at least when it comes to hydrogen isotopes, not necessarily oxygen, is the potential loss of lighter hydrogen isotopes to space through time over the last 4 billion years. Again, measuring water within really old rocks helps get around this because we don't have to take into account the last 4 billion years of Earth's history. But it's still a potential issue. So we have to take into account all of these potential issues and potential fractionation mechanisms when we look at isotope signatures. And we do, but there's still a lot to learn and there's still a lot to uncover. So I greatly encourage you to jump into this area of research if you're interested in this kind of thing. I will say it does involve a lot of mathematics, statistics, probability, modeling, etc. But where you can get a really great handle on these skills and have a lot of fun doing it, I might add, is Brilliant. Brilliant offers thousands of really fun and engaging and interactive online courses that don't feel like courses at all. You can learn about science like you do here on my channel, or even data analysis, data science, computer science, math, statistics, and all of those things that are really important skills for pretty much any job, but also just for understanding daily life and our daily interactions better, which I know if you watch my channel, you're interested in learning more about, our Earth, our planet, our daily lives, what we encounter, the science behind it. And that's what Brilliant's all about. I talked in this video about how Mars used to have a significant amount of water, and back when it had that significant amount of water, it might have had a significant amount of life that, has since gone extinct. We don't know. But on Brilliant, you can do a whole interactive course about terraforming Mars, which is pretty cool, and other astrophysics courses on there as well. Another thing I've been loving about Brilliant is just how short but effective the courses are. So if you want to check out all that Brilliant has to offer, you can go to the link in my description box below, that is brilliant.org/geogirl, for 20% off a premium Brilliant experience. And if you don't want to commit right away, you can get 30 free days of full Brilliant experience. So go to that link below and start learning right away. With that, guys, thank you so much for watching this video. I hope you will go check out Brilliant and see all that they have to offer. As always, my references are linked in the description box below, and I will see you guys in the next one. Bye!